squared dx, given that it's a Riemann sum. So we would get our little graph out and put a little dot here, put a dot here, put a dot here. This 1 is 1, this 2 is 4. So using a right Riemann sum, as you did for your homework, what would you get, sir? You didn't do your homework? 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. Oh, I said don't bother at all, didn't I? Okay, you're right. I lied. Okay, so do this. Do it on the right Riemann sum. I would go up the right side, across, down, up the right side, across, down. I get 4 times 1 plus 1 times 1, 4 times 1 plus 1 times 1. Agreed? And that would be a whopping 5. Is that an overestimation or an underestimation? Mr. Roebuck, it's an overestimation. We know that's too high. Agreed? Everybody agree with that? Mr. Roebuck, I've been foreshadowing this for long enough. I expect you to have the answer to this question. You ready for it? What if I wanted to make a better approximation using right Riemann sums? What would I do? Using right Riemann sums, what can I do to make my estimation closer to the right answer? You don't know? We got an idea? Well, I can't subtract the triangles because that would be like using triangle game somehow. Using a right Riemann sum, what would make it more accurate? Ms. B, you got it? Nobody's got it. Make smaller rectangles, right? Go ahead and just use 4 equal pieces instead of 2, right? So let's go ahead and do 4 instead of 2. Got it? Make sense? Okay, so if I were to sketch that, I would recognize that now I've got 1, 2. If I do half, half would be a quarter, 1 would be 1, 3/4 would be 9 halves, right? Put a dot there, and then this would be 4. But at least if I do right Riemann sums, this curve looks like this still, but now I'm losing less of the pieces, right? Does that make sense? Okay, solve that for me, and then we'll get back to talking about this a little bit more. Where's it going up? That's the real reason. The unreal reason that AP Central wants is right Riemann sums of increasing functions are overestimations. But you and I can agree it's because of little chunks on top. Agree? All right. Now that said, what would be better still? We're closer to the right answer. We know we went from 5. We're now at 3 3/4. That's closer. We know that's closer, right? We know that's a better answer. We don't know how much better. What would be better was still? Yes, sir. Make them infinitely, what are you talking about, man? Make them really, really small pieces. In other words, the more pieces I take, the better it's going to get, right? If I could shrink the pieces down to where their width was approaching 0, can't make it 0, right? Because that makes no sense. But if I could make it so it's approaching 0, then that would be the right answer, wouldn't it? So what are we talking about when we say we're approaching something but not reaching it? We're talking about limit. Whenever we get to a formal definition in calculus, we end up in the land of limits because we can't say what it is, we can say what it's approaching. And what it's approaching is good enough, right? Because we want to know what this thing's approaching as I pick more and more pieces. That would be perfect, right? What are we approaching? What's the answer as we approach? Does that make sense? Okay. With that in mind, we got to work our way through this. Now, this next part, I don't expect you to do. You need to follow it, though, because there's bits and pieces of it that you need to understand. The ideas you need to understand. What are the bits and pieces? Well, first thing we're going to do is we're going to write this for any number of pieces, because we want to limit as we approach an infinite number of pieces, right? And what we're doing is we're adding things, right? For that very first thing we did this chapter, we did summations. All right? Now I'm going to do summations as, and I'm going to double check to make sure I'm using the same notation I used on this thing. I did, okay, good. I equals 1, 2, well, since I'm not setting the number of pieces, I'm going to put an n up there. Do you agree? Okay. So now the question is, how do I get my pieces in this case? Mr. Cross, where's this half come from? It's the what? Not the area of the curve. There's a half times that. Give me the area for that piece, right? What's this half referred to that's in every single expression? The width, right? Now, how do I get it to be a half, Miss B? Why is it a half for this one, and why was it 1 for this one? What were you doing? We broke it up into pieces, right? We said that we broke 2 into 2 pieces, right? And we got 1. We broke 2 into 4 pieces, and we got halves, right? So it's 2 divided by the number of pieces, agreed? So 2 divided by the number of pieces is in each one of these expressions, no matter how many pieces we picked, right? If we picked 8, it'll be 2 divided by 8, right? Great, they'd each be a quarter. Good so far? All right, Mr. Roebuck, it's your turn. Where is this thing coming from? This little 1/2 squared. Where is that thing coming from? Well, we got a 1/2 squared, we got a 1 squared, we got a 3/2 squared. This is actually a 2 squared, right? Where are we getting those from? X squared. It's something squared. Let's start off with that. It's obviously something squared. How do we know how much is squared? And it's changing each time, right? This is 1 squared. This is like 2 over 2 squared. This is 3 over 2 squared. This is like 4 over 2 squared, right? So it's I. It's not I squared because that'd be 1 squared, 2 squared, 3 squared. It's I modified somehow, right? In the first one, it was 1 and 2, right? And that would work out nicely for me, right? Unfortunately, next time it was a half. Why is this one a half, and why does this one go up by 1s? Because the pieces are shrinking, right? And so it's basically, it's I times the piece, isn't it? And what was the piece? 2 over n. So the piece is 2 over n, so it's I times 2 over n. Nice. We did it without the step in between. That's the best way to do it. Okay, so does this work? So what did I get? I get I equals 1 to n, 2 over n, and I've got 2I over n squared. Agreed? Does this work? Do you want to do it for the 4-piece one or the 2-piece one? Let's do it for the 2-piece one because we're lazy. So if I plug it in, so I'm going to plug this thing in. So let me shrink this down a little bit so I can move a little higher. Oh wait, the 2-piece one answer was 5, right? Let's do it. Actually, it was 4. Let's do it. Let's do it while it's changing it. Here we go. Ready? So we're going to do from, since we're splitting it into 2 pieces, I equals 1 to 2, agreed? Therefore, this is 2 over 2. And this is 2I over 2 squared, agreed? So this first piece is going to be, so I'll plug in a 1. Actually, let me simplify a little further. I equals 1 to 2. This is 1, which goes away, right? This just becomes I squared, agreed? So when I plug in a 1, I get 1 squared. When I plug in a 2, I get 2 squared, and that's 5. 1 times 1, 2 squared is 4. It works. At least for the 2-case one. Do you believe me, or should we do the 4-case one? All right, you guys. I don't know if you believe me or not. But we'll move forward. Okay, so if that's the case, Miss B, we got a hypothesis what we want to do to this thing now that we've made it. What do we want to do to it? What do we want to make the pieces? If we want a best answer we can possibly get. Smaller. We want to take the limit as the pieces get to, not to 0. How many pieces do I want to take? It's already n pieces. Infinite number of pieces, right? I want to get an infinite number of pieces. So I'm going to take the limit as n approaches infinity. The number of pieces approach infinity. What is going to happen here? All right, so let's get some thinking done here. Okay, so am I having a weird moment here? Why am I having a weird moment here? I'm having a weird moment here. Hold on, pausing for my weird moment. Okay. Cheating. What did I think here? Okay, equal to 8 over n squared. Well, I'm taking the limit. Huh. Hold on a second. Pull this thing up when I figured out. I equals 1 to n. Again, you're not required to know this, all this stuff. Okay, so this becomes 2 over n. This becomes 4i squareds over n squared agreed. Right? The I squared needs to stay in, right? That's not going to change. So I'm going to go I equals 1 to n. I got to pull everything else out. This becomes 8 over n squared, n cubed, right? Agreed? Right? Because then n squared, n cubed comes out. And I end up with a 4 times 2 can come out, but I still got an I squared sitting inside. Agreed? I'm having a really bad moment. What the heck am I thinking wrong? Wrong thing, punished. Okay, so that simplifies that, right? You're still there? Okay, so on the very first expression, I asked you to look up. Oh, what? Yeah, I'm just going too early. That's my problem. I'm still going to take the limit as n approaches infinity. That's my problem. We got this. Okay, so everybody look up somewhere on that first expression. We did this, didn't we? On the very first worksheet. I said, you're going to need this later. Find it for me and tell me what it is. I got excited. Too much thinking. Very first worksheet, last problem on the sheet. What is the summation from 1 to n of I squared? What is it equal to? N parentheses? N plus 1, I think. Probably my writing. And then another 2n plus 1 all over 6. Agreed? Okay, so now I'm going to do a little bit more work. Limit as n approaches infinity. I got to FOIL up the top. Let's FOIL these two together first. Okay, so I've got 8 times n times 2n squared plus 3n plus 1 all over 6n squared. Agreed? N cubed. Agreed? Do a little bit more. Limit as n approaches infinity. I get 16n cubed plus 24n squared plus 8n all over 6n cubed. Agreed? Now how do I take the limit as n approaches infinity? Whose turn is this? Cross's turn, although he came up last. Good idea. Cross. There's two ways you know how to take the limit as n approaches infinity. One of them is use the L'Hopital's rule, which I don't particularly want to do here because it's a lot of numbers and it takes a while, and what's the point? Divide by the highest power of n, find anywhere in the problem. What's the highest power of n, find anywhere in the problem? N cubed, so I'm going to 1 over n cubed. 1 over n cubed. And I get the following. Limit as n approaches infinity of 16 plus 24 over n to the first plus 8 over n squared all over 6. Anything with n on the bottom goes away. 16/6, which is in fact 8/3. So the more pieces I take, the closer to an infinite number of pieces I get, the closer my area gets to 8/3. So what's the area? 8/3. If every step I make, if every amount of pieces I take gets me closer and closer to 8/3, then the area has to in fact be 8/3. With me? Well, that's the interesting part. When we did the formal definition for the derivative, we actually have to do that every single time. But what did we do shortly after we learned the formal definition for the derivative? We found a better way. If you want to really do an integral, this is the only way known to man to do an actual integral. That said, we're never going to do this again.